Sabbath. Good morning, our wonderful listeners, students, lovers of knowledge, parents, teachers, and more interestingly and particularly our students that regularly tunes in to Oxygen FM 96.9, where the station that informs, the station that inspires, the station that ignites. I'm your regular host. I welcome you once again to our educative edition of Physics on Here, your favorite program where physics come alive beyond classroom. I'm your host. For today, I remain your host, Kenny Badmus. We're going to make physics as simple as ABC, practical and interesting. On behalf of the production crew of Oxygen FM 96.9, situated on the Knowledge Hub 121-123 Obafemi Awolowo Way, Okeado Ibadan. I welcome you all to another exciting and transformative edition of the School on Air Physics on Oxygen FM 96.9, where our guiding philosophies remain deeply rooted or firmly rooted in education and enlightenment. So this education and enlightenment illuminates mind lesson after lesson. I remain your host, as I say. I'm Kenny Badmus, your pilot, and I'll be guiding you through today's exciting journey in the world of science. Behind the scenes that make smooth delivery and academic presentation is my producer, Mr. Olufemi Timothy Ogunyejo, who is vibrant and committed to this educational program, and above all, the studio engineer and ultimately the head of station, Mrs. Tokumbo Ishola. Thank you all for making today a reality. Students at home, you are welcome once again. The first segment of the program today is the Wisdom Capsule, as usual. The Wisdom Capsule is made around a notable figure in the world of physics. He is an Englishman. The history to the life of a remarkable English physicist whose discovery helped the world understand one of the most exciting and important ideas in physics, that is the relationship between energy, work, and heat. This is man by name James Prescott Joule, or JP Joule. His name is James Prescott Joule, or JP Joule. James Prescott Joule was born 24th December 1818 in Salford, England, and he died on 11th October 1889 after a useful 71 years on Earth. Joule was a physicist who made important contributions to the study of energy and heat. He is best known for demonstrating the relationship between mechanical work and heat energy. His experiments helped establish the principles that energy can be transformed from one form into another. In recognition of his contribution to physics, the SI unit of energy and work is Joule, which is symbolized by J. That was named after James Prescott Joule, JP Joule. So so students, I think you should by now imagine, having contributed immensely into the world of science, that your name becomes an embodiment or a part of a language of physics to be used by students and scientists all over the world one day. Thank you, and I remain your host. Yeah, welcome back. On segment 2, the core topic of today, or the main topic of today, is efficiency of machines. The topic of today is efficiency of machines. Last week, we were able to discuss work, energy, and power and their relationship. So, however, the importance of efficiency cannot be overemphasized, as there is a strong relationship between the study of work, energy, and power with efficiency. So efficiency of machines, this time we can now imagine around us having or seeing bicycles, seeing cars, generators, wheelbarrow, pulley, cranes, even scissors, to the smallest bottle openers. So these are simple machines from which we can understand the word efficiency. How does efficiency come into play when we see our machines doing their best, giving us support, helping to raise loads and position loads? So all this, like I said, will help us to understand today's lesson. So there's a big question that everybody should try to think about. Does every machine give back exactly what you put in? So does every machine give back what you put in? So is it a gigoting, give in, give out, or garbage in, garbage out? Is it possible? But the answer is strongly no, emphatically no. The answer is emphatically no. Because the first law of thermodynamics says that there is no perpetual motion machine. The first law of thermodynamics says that there is no perpetual motion machine. Or we say there is no machine of perpetual motion. So that invariably tells us there are associated losses with inputs, associated losses in machines. So when you put in, for example, if you put in 100 units of energy into the machine, how come can we have 100 units of useful energy? This is strongly not possible. So because there are losses associated. So students at home, please pick up your pen and jot down one by one. So what is a machine? What is a machine? However, we'll still come back to treat simple machine. But let's do it step by step. That what is a machine? A machine is a device that helps us to perform work more easily. So a machine is a device that helps us to perform work more easily. The machine helps us to multiply our force, to leverage. It's a way of leveraging. And by leverage, you get extension. And by extension, you are associated with distance. So machines can help us to multiply force. Machine can help us to change direction of the force by resolution. If you apply force at an inclined position, definitely there must be a resolution to the parallel. So machine can help us to increase speed. Machine can transfer force from one point to another. Machine make work more convenient. That is the main usefulness of machine, that we want convenience for what we do. And for instance, think about a wheelbarrow. If you want to move a heavy load, carrying directly may definitely be difficult, oftentimes difficult. But when you put the load inside a wheelbarrow, it makes it easier. So the wheelbarrow helps us to move it more easily, comparatively easily, and achieve more workload than using bare manpower. Let's also think about a pulley. If you want to raise a load to a higher height, there is a building construction around your place, 2-story, 3-story, 4, and skyscrapers. There must be a way by which concrete and useful materials are moved to higher heights for work to be accomplished. So these are why we have machines that are put in place to raise heavy loads vertically. So a pulley can help you change the direction in which you apply your efforts. So if you apply your efforts at an angle, it can help you to put your effort vertically or horizontally. So let's also think about a bicycle. When you apply a pedal force, the machine helps you to transfer the effort to wheel to produce motion. So machines invariably make work easier. Machine, as we've heard, that makes work more easier, or makes work easier. Don't let me the English people, don't let them catch me. So it makes work easier, or let's say it makes work more easy. So there's something very important for us to understand, that a machine, does it create energy? Does a machine create energy? A machine does not create energy. Energy can neither be created nor destroyed. That's the law of conservation of energy that we've learned earlier, that a machine cannot create energy because energy can neither be created nor destroyed. It only helps us to use the energy to supply in a more convenient and useful way. So this is, I repeat that, it only helps us to use the energy we supply. The energy we supply, a machine will help us to use it in a more convenient and useful way. So this is where the concept of efficiency comes in. How efficient is the process, and how efficient is the machine that we are using? So now, what is efficiency in real time? What is efficiency? What is efficiency? Efficiency in simple language tells us how well a machine converts the energy or work supplied to it into useful output. So it's like a comparison between the useful output and the input. So mark the word useful, not the wasteful. It's only the useful output that we are concerned with. The rest are transformed into another thing. That is what we call losses. Because some energy are lost, definitely lost. Where do they go? That's why we have the word, we mark the word, quote and unquote, useful energy. And I repeat that efficiency tells us how well a machine converts the energy or work supplied to it into useful output. So our concern is what goes in form of input, energy or work, and what comes out as an output, the useful ones. So a machine is said to be efficient when a large portion of the input energy becomes useful output energy. So that's invariably that anything over 50% becomes useful. Even useful 50% is still not good enough, but we're expecting anything in the range of 65% upward. That's when a machine becomes efficient. But no real machine is 100% efficient, like we said. Why? Why is there no real machine that is efficient 100%? We've been saying this all along. Because some energy is lost. Real machines are not 100% efficient because some energy is lost. Where do they go? Where does the energy lost go? Some of it may be lost through one. Please, students at home, note this, that the losses are due to friction. Losses of energy in machines are due to friction, 1, heat, 2, sound, 3, vibration, 4, air resistance, 5, deformation of machine parts, 6. I repeat that machines, energy is lost in machines due to frictions, due to heat, it may be due to sound, it may be due to vibration, it may be due to air resistance, it may be due to deformation of machine parts. Also, we can have distortion, you can have drifts, but primarily energy lost is through friction, heat, sound, vibration, air resistance, and deformation of machine parts. For example, when you ride a bike, not all the energy you provide through pedaling. When you pedal your bicycle, not all the energy you provide through pedaling is converted into forward motion. Some are used in gathering momentum, that is getting stability, and you put a lot of pressure to make sure that you are balanced on your wheel. Or maybe you've never had the experience of riding a bicycle. Yeah, I think I did that. So you got to use some energy to gather momentum, to stabilize. So once you stand firmly and there's no distortion again, then you now realize that what you put in becomes invariably easy. Your pedaling does not disturb your muscles again. It becomes completely easy. So, like I said, some energy is lost due to friction in the chain of a bicycle too, in the gears and the bearings, So some energy are lost. Those are mechanical losses. Some lost as a heat, and some produce sounds. So the machine cannot convert all the input energy into useful energy. That's where we are going. And we have a formula. There is a standard formula for efficiency, which is the useful output work divided by input work, or multiplied by 100%. Like I say, it's like a ratio. The efficiency is useful output work divided by input work, or multiplied by 100%. We can also express it in form of energy. That efficiency is still useful output energy divided by input energy, all in brackets multiplied by 100%. You see, the word useful output must be noted, must be observed. If you do not put it in the formula, suppose they ask you that what is efficiency, and you put output energy over input energy, you have not defined it. So because if you put the word useful, that's to say, you say machine is not 100% efficient. But if you don't put it there, you are trying to tell the world that what you put in is what you get. That's saying that we're likely to have 100% efficient machine, which is not possible. So the word useful must be noted as quotes and unquotes. Let's start with an example. We have two examples. I want to treat two examples here, which is as simple as ABC. Now, let's take it to practical. I said this session is enlightening, is practical, is real life. So we solve real life problems here in terms of our discussions. So let us take an example, a practical example. Imagine a machine receives an input energy of 500 joules. A machine receives an input energy of 500 joules. After operating the machine, only 400 joules becomes useful output energy. So then what is the efficiency? What is the efficiency? In fact, I know of primary school pupils that would do wonders. They will get this for us. So because it is simple that useful energy, output energy, divided by input energy, all in bracket, multiplied by 100. So when we have the useful output energy to be 400, now you divide it by 500. Brackets, and you multiply by 100. That is invariably 4 over 5 times 100%, which is 4 times 20, which gives us 80%. This is a purely efficient machine. A purely efficient machine with 80% efficiency. But what does this mean in real analysis? It means that 80% of the energy supplied to the machine is converted into useful output. However, the remaining 20% is lost in a way, such as friction, heat, sound, and vibration. I remember when we were younger, small, let me say, when you go to the milling people, Yalata, the environment here, Babelero, you went to mill your maize for pap, for example, or you went to mill your pepper. And when you come back home, your mother sends you back and say, "What is this rubbish you have brought to me? You are an idiot. Don't you see that this one is not milled? It's not well, it's not fine, it's not smooth, it's not pulverized." Then you look at it. You look stupid. How do I know now? Don't you touch it? When you are doing things, you don't put your mind there. That's to say, the machine has lost its useful energy to losses. That's why you see, Yelero will tell you, ẹnu ti bàjẹ́. You know, that's to say that the process is not good as it is. So there are losses to friction, and a lot of things do happen in milling, so that we may be beyond our scope. So let's just put it like that for laymen to understand what efficiency is all about. An example too, also, that suppose we have a machine that has an input energy of 1000 joules, but the useful output is 700 joules, for example. So we don't need to go far off that this is 70% efficiency, because the useful output is 700 joules divided by 1000 input energy, all multiplied by 100%. So it gives us 70% efficiency, which is good, very good. It's a good machine. So Why are machines not 100% efficient, like we said? So the major reasons is energy loss. Energy loss due to frictions, like we said. Energy loss due to friction. Friction occurs when two surfaces move against each other. For example, inside a machine, like I said, the milling, you see there's this plate that is how best can I put it? It's round, it's circular. You can see the shape of the inside of the milling machine. So there are two plates that are often together, but they are marked with stripes. So that stripes is to enable them to rub together so that objects coming in can easily be smeared and pulverized. So that is wherever these stripes had been worn, that's the laywoman will say erotic badge. So that the stripes had worn. The stripes had worn. They are iron. So once they are worn, there's no efficiency again. That's where friction comes in. Another is the loss associated with sound. That's more of mechanical and electrical. When machine operates, you may hear a lot of noise. So there's something wrong with the electrical and mechanical system. If the bearing is not good, humming and all that gives notable sounds, it becomes a useless energy for the machine. That sound carries energy away from that system. Another source is vibration. When there is vibration, there is instability. Even as a man, if you are not stable, if you stagger, you cannot hold things. That means the efficiency is going. I won't learn here. So, long go show ambe. Well, let's go back to the business. So some machines vibrate when they operate, and the energy is transferred into vibration. There are many also that there are many losses due to air resistance too. So for a moving machine like a vehicle, if there is sometimes rains is trying to fall and you see a lot of air drift around, wind and all that, if a vehicle wants to move around, of course, definitely a moving machine will continue, a vehicle will continue moving, on the road. But when it encounters serious air resistance, it has to redouble its speed so that energy can be increased, or it maintains that energy and gets a reduced output. So that is invariably the loss of energy is a transfer of energy or transformed, because energy can neither be created nor destroyed. That's the law of conservation of energy. You're welcome back once again. So next is, how do we improve efficiency? Very, very important. How do we improve efficiency? When there is a problem around the machine, how do you improve on its efficiency? Because you need to have useful output of energy and work. So if friction is one of the major causes of energy loss, how do we reduce it? We can reduce that by lubrication. So we can apply oil and grease. Where you should put oil, you put oil. Where you should put grease on the moving parts. Not swapping. Putting grease where oil should be and putting oil where grease should be. That's not productive at all. So to the contact parts, you apply oil where oil is to be applied, and you apply grease where grease is to be applied. This reduces the friction between the surfaces. Proper maintenance, number 2. It's very, very vital. So you see, so a machine that is regularly maintained, like a motor vehicle now. Use your motor vehicle, most of the commercial motor vehicles on the road. How often do they change the oil of the engine? So those are areas. How often do they change the oil in the brake oil? How often do they change the gear oil? Brake oil, gear oil, engine oil. They have definite time for changes or mileage that you must have gone. So once you notice the mileage, that it has reached a specific number which is already advised from the manufacturer, so you change the oil. So as much as you change the oil, you are improving the efficiency of that machine. So good design, number 3, that's on the part of the engineers. So that's why you see research is going on day by day. All these are invariably in ways to improve on designs by innovations, changing what to another to improve efficiency, to improve to reduce losses and to reduce wastes in our society. So using suitable material, that's number 4. Not using adulterated materials. Standard materials are meant to be put, or the right material and standard have to be put in place. This is to avoid friction, vibration, and other forms of energy losses. So the right suitable materials has to be used. Proper alignment, that's number 5. So you align what is supposed to be put, align 2 things or more together. When machine components are properly aligned, when there is a hub, you know what to put there. Don't improvise with the wrong material. Okay, you want to change a system, a machine, you now say, okay, since we cannot get new parts, maybe we use Tokumbo. Well, Tokumbo also very, very good, but there are times you don't get Tokumbo. You now have to go to a miller or a welder. Please, Ebawa raw, try to adapt it for us. So adaptation may not be. There is what they call the word adaptive technology in engineering. That one is different. But about our raw system, that's to say you are reducing the efficiency invariably. So proper alignment, like I said, number 5, when machine components are properly aligned, energy losses are reduced. So students, remember, a well-maintained maintained machine is usually more efficient than a poorly maintained machine. Welcome back once again. So now let's try to put together the knowledge of efficiency with simple machines that are concerned subjects of interest. The concerned subjects of interest in simple machines are mechanical advantage and velocity ratio. Mechanical advantage, velocity ratio, and efficiency, they all go together. It's like a synergy. So in simple machines, we must not confuse these 3 terms. It has to be clearly defined. You must know that mechanical advantage, velocity ratio, efficiency are subjects of interest in simple machine. What is mechanical advantage? So the mechanical advantage tells us about relationship between load and effort. So the mechanical advantage tells us about relationship between load and effort. So mechanical advantage is still like part of efficiency, because when you talk of effort and load, you are still talking of input and output. So Velocity ratio too tells us about the relationship between the distance moved, because we want to make work easier. We use a wheelbarrow. You have leverage by trying to put a distance across your efforts so that you can carry more load. So through it with a basket. So efficiency too tells us how effectively the machine converts the input work into useful output work. So there is a relationship between them. There is a relationship between them. Efficiency is equal to mechanical advantage divided by velocity ratio times 100. Efficiency is equal to mechanical advantage over velocity ratio times 100%. Efficiency, I repeat, equals mechanical advantage divided by velocity ratio times 100%. That's efficiency equals MA over VR times 100%. So suppose, for an example, suppose there is a mechanical advantage of the mechanical advantage of a machine is 4 while its velocity ratio is 5. So then what is the efficiency? So the efficiency is mechanical advantage, which is 4, divided by velocity ratio 5 times 100% gives us 80% straight off. So let's repeat that. That, for example, if you have a mechanical advantage of 4, a velocity ratio of 5, the efficiency will give us 4 over 5, 4 divided by 5 times 100%, and that gives us 80% straight off. So the machine is 80% efficient. Now, there is an important point. For a real machine, mechanical advantage is usually less than velocity ratio. So note. So wherever you see that a mechanical advantage is greater than the velocity ratio, please try to put a caveat. Watch. It may be a wrong application. However, there are situations like that. But mostly in real machine, mechanical advantage is usually less than velocity ratio. MA is less than VR, because some energy definitely must be lost. So it goes back to what we have said earlier on, that no real machine is perfectly efficient. So in life application, efficiency is not about doing more work, doing hard work, doing more work, adding to your input. It's about wasting less of what you already have. This is a practical example of life. It's more general. So let's think about it. It's not only in physics, but in physics, a machine is efficient when it converts a greater proportion of the input into useful output. We've said that earlier on, that a machine is efficient when it converts a greater number of input energy into useful output. So in life, the same principle goes to you and I. Students at home, please remember, when you have time, don't waste it. When you have talent, don't waste it. When you have knowledge, apply it with wisdom. When you have opportunities, embrace and use it wisely. But if you waste them, you are not being efficient, invariably. That's to say, time, talent, knowledge, and opportunities are for us to be used reasonably. Those are our inputs. And what comes out of it is the useful output. So the wise person does not only ask, what do I have? The wise person always asks, how well am I using what I have? So when you have knowledge, how well are you using it? When you have time, how well have you used your time? When you have talent, how well have you using it? Have you used it? So a student who has 1 hour to study but spends 40 minutes aimless, distracted, he has not used his time, his available time efficiently, definitely. So he or she has not used his available time efficiently. So that's to say, losses is more than the useful energy. So whereby another student who uses the same 1 hour wisely will definitely achieve more results, even much more. So today's physics lesson is science, is real life, it's practical, and it's interacting. So let's also reduce our waste, maximize our usefulness, and improve our output. Just like engineers keep working on how to reduce friction, energy losses in machine, so we should identify those gaps that's where our energies, our inputs are being wasted. So students, do not waste your potentials. Don't waste your time. Don't waste your opportunities. Don't waste your knowledge. Use them wisely. I want to have a quick revision for us. And the studio line is now open. 070 4700 3969. 070 4700 3969. 070 4700 2969. 070 4700 2969. So, coming back to revision. So welcome back. Before we go, let's quickly have a revision. However, this topic cannot be completely treated without going back to simple machine purely. So coming next week, by God's grace, we will be going to simple machine purely, where we treat mechanical advantage separate, velocity ratio separate. What are the formulas that are associated with each of the two, and how we come back to the word definition of efficiency as mechanical advantage over velocity ratio times 100%. So we are coming back next week because of our time. We cannot finish everything. So even in simple machine, we have to study mechanical advantage, velocity ratio, the lever system, and a few others. So by next week, God's grace, we'll be doing that, meaningfully. So our revision questions goes thus: that what is a machine? What is a machine? Studio line remains open. 0704700 3969. 0704700 3969. 0704700 2969. 0704700 2969. So, like I said, what is a machine? As a review, a quick revision. That what is a machine? A machine is a device that helps us to perform work more efficient, more easily. A machine is a device that helps us to perform work more easily. So, and what is efficiency? Efficiency is the ratio of the useful output work or useful output energy to input work or energy expressed as a percentage, that is multiplied by 100%. So, can a real machine be 100% efficient? No. Generally, we said no, because some energy is lost. So we need to understand that we need to mention one cause of energy loss. At least one. Friction, vibration, sound, air resistance, These are various ways through which energy is lost. How do we reduce friction? How do we reduce friction? It's proper lubrication, maintenance, proper alignment, among others. So, what is the formula for efficiency using work or energy? So, the formula for efficiency is the useful output divided by the input multiplied by 100. These are recaps. So, what's the relationship between mechanical advantage, velocity ratio, and efficiency? So, the efficiency is the mechanical advantage divided by velocity ratio multiplied by 100%, or expressed as a percentage. Welcome back again. So, like I said, by next week, God grace, we'll be treating simple machines separately and continuously. Simple machines separately as a non-powered device. And there are 6 classical simple machine examples. We will treat them one by one. So where the word lever system, pulley, wheel and axle, inclined plane, others come in. So how they are associated with efficiency, losses, formulas, mechanical advantage, velocity ratio, and that. So I remain your host. Towards the close of the day, we are still on your weekly exciting edition of Physics on here on Oxygen FM 96.9. Here today, we've been able to assess the word efficiency, the topic efficiency of machines. So we've learned machines that machines help us to perform work more efficient, more easily, or more conveniently. But real machines cannot convert all input energy into output or useful energy due to losses. So towards the end of the day, I want to appreciate my studio manager, Debbie. I want to appreciate him for the good work. My producer, Mr. Olufemi Timothy Ogunyejo, and the head of station, Mrs. Tokumbo Ishola, and all our engineers who's making everything possible to ensure that we are live on here and everything is in place. So we also learned that efficiency cannot be improved on. Okay, that's a message for us here. Okay, thank you. Adekunle Ojo Christiana says good morning. Okay, another one says more strength to you, sir. Thank you for joining Oxygen FM. We love you all. Thank you for being part of us. So remember that we keep asking questions, we keep exploring in our daily lives and activities. And remember that physics is not just a subject in your textbook. Physics is an all-round or all ramification practice, daily practice. That's what you see around us is physics. What you touch is physics. How you move is physics. Remember, nothing moves without emotion. Nothing works without emotion. That invariably says that physics is life. Physics is life. Until our next edition of Physics on Here, I remain your host, Kenny Badmos. Keep your minds open. Keep your curiosity alive. Keep learning every day. This Physics on Here, coming to you right from Oxygen FM, the station that informs, the station that inspires, the station that ignites. Thank you. See you next week. Breathe in the beat, breathe out.